Okay, I think we'll start. So we'll have a new topic today. We are now leaving shipping for a while and we are going into offshore technology. And I'm going to talk about offshore platforms today as well as I think most of next week. So it's a big and a very comprehensive topic. So we'll have to spend some time on it. I think I mentioned to you before that maybe Korea has not been all that successful in the area of, let's say, building offshore platforms and so on. So maybe we can get some better insight into what it's all about, and then you can do something about it, right? So I'll give you a little bit of background, and of course the driver, and we often talk about driver, what's pushing the development, and the driver, of course, is the need for energy. So we'll have some statistics about energy and how that is evolving and how that is being projected for the future. We're going to talk about types of platforms and other types of offshore installations. And as usual, I will focus on safety as a very, very important aspect, and a little bit about trends and the future. So I think the oil history goes back to 1850s and so on, when they found out it was possible to burn that black liquid that was found in the ground some places where it came up naturally. So the oil mainly started on land, but of course gradually moved towards shore. And for instance, in the Gulf of Mexico, very much of the oil deposits are associated with the Mississippi River Delta that goes far out in the ocean. So gradually one had to go into the sea in order to find more oil. And similarly, other places where the oil was very close to the surface, like in Azerbaijan and the oil capital Baku and so on, they gradually moved into the ocean to find the oil, but not very deep into the ground. And of course, in Netherlands and the UK, the oil and gas history started in the North Sea. So very primitive platforms in those days, and typically in shallow waters, right? So when you have shallow waters, it's much easier to build structures. And the challenge that we're going to talk about in today and next week has very much to do about the challenge of going into the deep ocean. So if you look at oil production, and this goes back to year 19,000, so more than 100 years back, all the way up to where we are about today. Of course, I think this graph was made in the year 2004, and things have not gone down quite as much as was indicated in this picture. But I think what is interesting here is year of peak oil. What is peak oil? That's the peak production, the maximum production, right? So you find, Canada, Romania in 76, Indonesia 77, Egypt, India, Syria, Malaysia, Argentina, Ecuador, United Kingdom, Australia, Oman, Norway. About, well, not quite correct actually, because I think it was last year. Yes.
Why there is no Middle East country?
Yemen. It should be Oman, but of course the United Emirates and Saudi Arabia. It must be here.
Saudi Arabia is low.
Where is Saudi Arabia?
There is no Saudi Arabia.
Mexico, I don't know. That's a good observation. Texas, Alaska. Okay, well you have to. That's a good observation. So we have to figure that one out. Yes.
I wonder maybe this data contain showed only the official oil as well.
Yeah, but isn't Saudi Arabia official?
As I know, the Saudi Arabia share no official production facility.
Yeah, but this is not only offshore, Yes? Okay. Well, I was able to get some very, very recent statistics from the International Energy Agency, this year's report. And so some of the figures are up to last year. But this graph shows the energy mix. If you look at the total energy supply, I should get my pointer. The total energy supply, and it's coal, hydro, oil, gas, nuclear, combustion. That's wood and waste. And you see oil is about 33% and gas 21%. So oil and gas together is 54%. And then you have coal, which is the large piece of this cake, and nuclear less than 6%, and so on. So this is typically firewood and that sort of thing. And what is interesting also is that there is the renewables that are not wood, the other renewables, which is 0.7%. And what is that? Geothermal, solar, wind, heat, etc. 0.7%. That's as far as it's come. Of course, there's a lot of attention to that topic of solar energy and wind and current and all that, but it really does not yet matter very much in the energy picture. So what comes to my mind is, if we were able to be more efficient in our use of this and use less of it, the environmental effect of that would be much greater than what we at present, can obtain here. So even with a 5 to 10% growth in that sector, it's still going to be very, very small for many years to come. So the cleanest, that's what I like to say, the cleanest energy there is the one that you save. Right? Absolutely clean, the one you save. You're not using anything, right? So certainly also hard technologies are very important for the environment. Okay. At least here we have the Middle East, right? Maybe you can convert that other graph to the same units as here. So this is million tons of crude, right? And here you see OECD countries going down, Middle East, former Soviet Union, etc. So Africa is increasing, right? So you see how that is shared more in detail for year 2009. So this is very, very recent statistics. Yes?
What is
Is the Organization of Economic, it is, let's say, the developed part of the world. So it's Europe, but I think Korea, for instance, is a member of OECD. And you can go into internet and see what countries are members of OECD. But it's essentially the developed countries. Okay, and here you have it also with the crude oil. You see the main producers, but many of them use a lot of the oil themselves and don't export very much. United States is still the third largest, but when it comes to the exporters, they are not on the list, right? On the other hand, they are on top of the list of importers. And this is something that worries, of course, the authorities in the United States, that their security when it comes to supply of oil is very, very poor, right? So if there were to be a major crisis, they would have very large problems. And of course, by more or less connecting exporters and importers, you have really the basis for shipping of oil, right? So that is the figures here. Okay. So that's crude oil. So Korea is a big importer of crude oil, as you can see. But what is really influencing the market now is what's happening in China. And they are going to be even bigger. And since we have very often we meet statistics with different units, I made this one. Of course, in the SI system, we have very easy conversion of units, regardless whether it's energy or it's something else. So the basic energy unit is a joule, as you know. And its mass times acceleration, and it's the same as also a watt second, right? A joule is 1 watt second, so it's very easy to convert let's say, the thermal energy in fuel into other units, and look at the equivalence. And 1 ton oil equivalent you can convert into, it's defined as 10 gigacalories, which is this many joule. A BTU is often used, British thermal unit, and you see this figure. And a cubic foot natural gas. Sometimes we see cubic foot and sometimes we see cubic meter, and of course it's not difficult to convert from a cubic foot to a cubic meter, and there you have also the caloric or the thermal energy content. So I'm sure some of you will be working on energy in your student projects, and this kind of conversion is good to have. Natural gas producing countries, Middle East, former Soviet Union, here you see, and this, like the graph on oil, there was a kind of a kink from 2008 to 2009. Of course, some of that may be due to the financial crisis, right? But it also is an indication of we are peaking totally when it comes to oil as well as gas. Yes, sir.
Is there any producing countries, I mean, natural gas producing countries
Except for Qatar? Well, there are many. Here you have it. So I anticipated your question, right? You have producers, right? Net exporters and net importers, right? Here you have the big producing countries, right? So Russia is certainly the biggest by far that is as an exporter, because the United States, of course, uses most of this gas itself. I think they send some gas maybe to... No, they are not. They are not on the exporting. They are not on the exporting side at all. US get much of its gas from Canada and from Mexico. But as you see, little Norway is the second largest gas exporter in the world. And we almost export all of it, right? Because we have hydropower. So Japan is the biggest importer. But again, I think I'm surprised not to see China on this importer graph. But I think they'll be there very, very soon. No? Yeah, we have 106 billion cubic meters of gas produced, and we export 100. So we use very little, and that's mainly for the chemical industry. We don't use gas for heating or anything like that. But we start using it for ferries, and I think I mentioned to you establishing the distribution system for LNG, because we produce LNG as well as export in pipelines, right? Of electricity, 98.5% comes from hydropower. It's a very unique situation. We are blessed. We are blessed. U.S. oil production and imports, right? This is oil production. Look at that. It's going down very rapidly. They are not finding many new resources, and the Gulf, as well, the Mexican Gulf as well as Alaska, is producing less and less. And then you see the imports. And the consumption is going up. This was the oil crisis, right, in the 70s. Look at China. This is something that is worrying the international community. That China is, of course, there are so many people and the standard of living goes up. So it can be expected, but of course it that strongly influenced the international price of oil. So this is one of the predictions, and there are many predictions that we are close to the peak of oil production now. You see that? But you know, if you go through history and look at typical, predictions, one has, let's say, this is the production curve, and then the prediction curve comes like this. And then a few years later, the graph may be looking like this, and the prediction looks like this, right? And then a few years later, maybe the production is like this, and the prediction is like this. But why is that? Of course, there is more efficient production methods, so one can get more out of the reservoirs, and there are new reservoirs being found. Some are shut down, but more has been found and put into production. But now we are reaching peak. So even though before we have all these predictions that the end is near, so to speak, now it's going to happen. I don't think it's going to be as dramatic as you see on this. This is a site that's called lifeaftertheoilcrash.net. Life after oil crash. But so some comments. So that's really what I was showing here. Production predictions have always pointed down after a few years into the future. Now it's for real, because consumption growth is larger than the production increase. It is real. The US is running out of oil. That we saw from the diagrams, right? Some oil and gas producing nations are highly unreliable. You know what happened in Europe, for instance? We had a crisis with gas delivery because some disputes in East Europe, and the Russians shut down the pipelines supplying West Europe with gas. So, and of course there may be conflicts that could influence also. So higher cost of oil and gas is inevitable. I'm quite sure about it. We are now around $80 per barrel of oil, and it's going to go up. For a short time it was up to 100 and what was it, 25? Then it went down again, but a couple of years ago. But oil and gas is going to be more expensive. And one can say one positive side of increasing oil and gas prices is that it becomes economically feasible and profitable to develop the smaller reservoirs, right? Going deeper into the ocean where the production cost is much higher. So if the market price is high, one can also afford developing fields that are more expensive. So in one way, the price is a driver for being able to produce more. So for instance, small fields, very often referred to as marginal fields, remote fields, far from markets, deep water fields, and of course Arctic regions. And some estimates now say that about 25% of the remaining reserves of hydrocarbons, oil and gas, are to be found in Arctic regions. So as we saw from some previous statistics, oil and gas stands for 54% of the world energy production. About 30% of the oil and gas production takes place offshore. So this is already very, very big. It's estimated that 50% of undiscovered oil and gas lying offshore. That's because, of course, initially one did this on land, and the reserves on land are being fully exploited, right? There's less left there. So what is the reserves, which has not been produced, is the share of that is increasing, and it's estimated now that 50% of the remaining oil and gas is offshore. So it's quite clear this is going to be very, very important, not at least because it's so necessary for modern societies to have oil and gas, right? And we have to go into deeper water, deeper and deeper. So we're going to get into different types of platforms, and today we are mainly going to talk about fixed platforms, and this is, a space frame structure, and it's often referred to as a jacket platform. That is the terminology that is used in the oil and gas industry. Jacket platform. So if you you use Google and look up jacket, what you mainly find is new concepts in jackets. You find this. But anyway, that's what it's. And then there is compliant tower. That is for very deep waters, and that is when you realize that the structure will have large deformations. You kind of let it have large deformations. Here you see the main members of the structure standing like this to make it stiff in the transverse direction, horizontal direction. Here you see it's like this, and it will have larger deformations. But one can put the equipment on board that will allow that. We're going to look at what is called tension leg platforms. This is one concept. Then there are many types of floating production systems that may be. Another name that's used is semi-submersible, and that semi means half. It's half into the water, so to speak. Then we have what's called also a tension leg platform, different type than that. subsea systems. The subsystems are systems that are standing on the seafloor. And then there are different types of deep buoys. A buoy, you know that expression? It's a floater, right? A buoy can be just a plastic bubble or ball that is used for tying up your yacht, for instance. But, you know, this is a deep buoy, a deep floater. And there are many different types. We're going to look at some of these. Here you see jacket, compliant tower, also a TLP. Here you see also a TLP. Different from, you see the difference between these two? Here you have a very small water plane area. Here you have a larger water plane area. Here you have a semi-submersible floating production unit. Spar, truss spar, another spar. So there are many variations. FPSO, we'll talk about floating production, storage and offloading. But this is also semi-submersible, half submerged into the water.
Professor, what's the formula of control?
Of
Control, what's the formula? Next to FPSO.
FPSO, what this? A buoy? Yeah, this is just, it can be, let's say, weather observing buoy. It could be a military buoy. This is a buoy, right? This is a deep buoy that's often referred to as a spar. So there is a certain terminology that is used in this industry that you have to get used to. So here you have it. You have fixed platforms. They are attached to the seafloor. Jackets, right? We talked about jacket platforms. Concrete gravity platform. And obviously a gravity platform is a very heavy platform, and it stands in its place because of its weight. Earth-filled platforms, artificial islands, you find particularly in the Arctic. Compliant tower we talked about. Floating platforms that are both floating and can be fixed. Jack-ups. We'll look at that too. Semi-submersible platforms, steel and concrete, tension, TLPs, tension leg platforms, spar, deep buoys, big buoys, barges, and there are ship-type structures too, for drilling and for production and storage. So, main functions: exploration, drilling, looking for oil reservoirs. It's the production, it's storage function, you store oil on board. Processing, very important also. Nowadays we are talking about offshore processing of LNG to make LNG plants that are floating, right? Housing, of course, foundations for various offshore installations. So, if we are to work in this field, there are many things we have to consider. So, if you are working on innovation concepts for offshore platforms, what do you have to think about? Well, of course, you have to think about, I should have listed that too, that's possible to build, of course. And then it's transportation phase. It has to be stable in transportation. It has to be feasible to move it. Then it has to be feasible also to install it. Then we have to look at structural performance, static deformations, dynamic response, vibrations, and then of course what's happening with the material in terms of fatigue. We're talking about low cycle fatigue, and that is when maybe you have a few thousand cycles, but with plastic development, right? And then if you really go into the plastic zone, then typically steel will not be able to take very many cycles. Then we have also high cycle fatigue, and because the loading is wave loading, we can reach into the millions of cycles for a structure during its lifetime. If you think of a wave period of a few seconds, and the structure is going to last for 30, 40, maybe 50 years, you get into the millions of cycles. So fatigue is maybe the most challenging design condition for offshore platform. Stability and ultimate load capacity. Safety. What is the system redundancy? That is, if one part of the structure fails, will the whole structure collapse? That's what's called redundancy. I'm not, if you have structural mechanics and statics, you know what a redundant system is, right? That is when you have the force distribution depends on the relative deformations, because the forces can go many ways. And in one way that is an advantage. If you have a structure where one member is failing, you can redistribute the forces within the structure, and that's what we call redundancy. So there are extreme conditions. You have to consider some sort of failure associated with this: storms, fire, explosions, collisions, earthquakes. And in safety context, of course, also evacuation. Then it's altogether the functional performance and capacity, the production capacity, the storage capacity, and what is called maintainability. How easy is it to maintain? Far out in the ocean, deep into the water, and service altogether. And of course, it's the economical part of it as well. So, just to give you an understanding of that, we are not talking about a few structures here. Look at this picture. This is from the Gulf of Mexico, and this is the Mississippi Delta Formation. Okay. Here we have 500 active platforms in the western area. Here we have 3,300 platforms. It's incredible, isn't it? Of course, most of them are in shallow waters, but some of them are now down to 2,000 meters of water. Of course, not the fixed platform, floating platforms. So this is a big industry, and the main hazards: hurricanes. For instance, some of these hurricanes have created a lot of damage. Some platforms have toppled, gone over, and failed during hurricanes. And of course, one can also worry about collisions when you see how many platforms there are. So, a little bit more about the more specific platform types. So it's jackets is the majority of platforms today, 80 to 90%. And typically we have tubular steel members, tubes, the main legs that are often referred to as cords, and then you have the cross members to stiffen the structure. And a structure may contain many hundreds of members, complicated joint. Look at this. Obviously, it takes experience and special competence to build this kind of structures. And the main concern is to not only to be able to build it, but to design it in such a way that you don't get fatigue problems. So the joints are particularly critical. Large platforms, difficult to install, that is launching and uprighting. I'll explain what that is. Then they have to be piled. You know, to be able to stand in one place, you have to pile into the ground. And fatigue is the #1 concern in a design context. Yeah, there are some, I'm not sure how clear this is, but you see here what's called the main chords, and you see typically the conductors. This is where you extract the oil from the reservoir. Here you have a drill tower, and of course you also have to replace parts of the pipes at times. This is the piling I talked about, and then of course you have different processing on board, and you have export lines, right? After you, for instance, separate out the water from the oil, and then you export it. This should give you a feeling of how big these platforms can be. So there are fixed platforms, I think, down to about 500 meters. Look at this. It's enormous. And I've seen another picture, I wasn't able to find it now, but I've seen another picture of, I think probably this platform, with a 5-story building next to it. You know, it looks tiny, little thing, compared to the platform. This is not so easy to see. What you see here is a barge. This is the platform lying on the barge, like you saw on the previous picture. And this is simulation, where you have the barge, you have the platform on top, and then you slip it off, and the back end comes last, and it goes into the water, turns around like this, and sets down to the seafloor. Very complicated analysis, but that's the way they have to do it. So launching, installation, then afterwards putting on the processing, and as you can see, it can be very, very complex type of processing equipment on board, very heavyweight, etc. Well, that this is what's called offshore operations, and during this operation, where you have to put it down in the right place. First, it's like this, and then you can ballast it so it goes down, right? But in that operation, you have several tugboats that keeps it in position with GPS, etc. So that's what's called dynamic positioning, and they can set it down, within centimeters of where they want it.
Is there any software that you use that option? Is there any software?
Software for this? Oh yes. Oh yeah. I had one doctoral student who worked on this type of problem. So it's yeah, you need it. There was when you ask, was one case in the North Sea where they came out with a brand new jacket platform, and they they let it go in, and then it started like this, and then it went plop, 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 and it sank. And what happened was that, when you do the uprighting, you have floating elements, which are almost like pressure vessels, right? But the pressure is from the outside. And some of them collapsed because of the water pressure. They hadn't been designed properly, right? So the whole platform, maybe costing $50 to $100 million, went down because of an analysis mistake, right? They hadn't really done the shell buckling problem properly. So it's, to find the motion and also to do the proper analysis of when you see how much, for instance, the floating elements are submerged, then you have to do a proper design. I think you can, if you search the internet, and I didn't include it here, but you can find some videos showing this launching process. And when the platforms become old and there's no more oil, they have to be dismantled. So you have big operations also to remove the platforms. And it's, of course, in the future, very many platforms will have to be removed. Thinking, for instance, of the Mexican Gulf, where there are thousands of platforms. They will have to be removed. Then we're talking about gravity platforms. I'm just wondering, I'm now at slide 26. Are you in a hurry? Do you have 5 more minutes? Okay. So this is concrete platforms, and this was the first concrete platform that was built in the North Sea on the Ekofisk field. It was started construction 72, 73, and it was really planned as both for production and for storage of oil. Later on they had to build an extra wall around it, so it was kind of added, and now it's mainly used as a base for other platforms in the neighborhood. But I remember discussions regarding this platform because, you see, they added an outer wall perforated to protect the inner part. But of course, when you have an outer wall, you also have a large diameter of the entire platform. So the total, inflow of current and waves is increased by the protection wall. So there is some discussion if it's smart to do, to have a large water area, maybe for stability, as opposed to having a smaller one where you get smaller forces. But that was the first. And of course in Norway we developed the concrete technology. And this is the biggest concrete platform called the Troll platform. It's 470 meters high. So it's standing, as far as I remember, at a little bit more than 300 meters. But then, of course, you have the distance up to the deck. You have a large deck, and you have things on top of the deck. It's enormous. So you see the Eiffel Tower here. It's small compared to this. And but the thing is, nobody has seen this one, right? No, nobody has seen it. Well, somebody has seen it from the inside, but not from the outside, because it's built on water. Very interesting to do finite element analysis with millions of degrees of freedom. Supplies 10% of Europe's Europe's gas consumption. It's a very important platform. So it was expensive, but it is serving extremely well. Yeah, this is some other comparison of size. This is very briefly how they are built. First you build the lower part in a dry dock, then you float it out. This is what's called the caisson part, the lower part. They are essentially connected cylindrical shells, and here you see the capping on top of it. So it's a spherical shell on top of a cylindrical shell, and then you have these shafts, some extensions of these cylinders going up to support the platform deck. So it's built floating on water, and that's why I say that nobody has seen the entire platform at one time, because it's always been on water during construction, except for the very base in the dry dock. Yeah, here you see some more pictures. And of course, critical phase is when you come with a deck, prefabricated deck, with all the processing on board, and this is put on top of that. So now the platform is 300 meters underwater here, and just a small 10 meters going up here, and you put this, I'm not sure, 30,000 ton deck on top of it. And that's the advantage by a concrete platform, is that you can put the deck on top of it while you are lying here in the fjord. This is a deep fjord in Norway. So you can put the deck on top and then take the whole thing out to location. And that's what you see here. You see all these tugboats? And actually there are some tugboats pulling in the opposite direction too. I think there were 11 tugboats to take it out. It's enormous. So that's a big operation. So that was the last one I think I have today. So it's said to be the world's largest man-made movable object. So bigger than the ULCCs, etc. So quite an engineering feat, and this shows, if you have the theory in order, if you know enough about the ocean climate, enough about materials, enough about structural design, you can do things like that. That certainly at one time was a first, right? You had to, since this cost maybe $1 billion, you have to be sure that you have done everything right. So that is really innovation in practice. Okay.